Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. This is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Linear Algebra, and it is related to a linear map from the polynomial space to matrix space. This question is placed in part C, which is a multiple select question. There may be more than one answer and it carries 4.75 marks. The question ID is 706552. Further, this question is suitable for all these examinations. Right. The given question is, for each n greater than 1, let V be a R vector space of all n by n real matrices and A belongs to V be invertible. Consider the R linear transformation phi from Rx to V such that phi of x power k is equal to A power k for all k greater than or equal to 1, and phi of 1 is the identity matrix of order n. Which of the following statements are necessarily true? We are given 4 options. Option 1, phi is 1 to 1 but not on to. Option 2, phi is on to but not 1 to 1. Option 3, there exists a function f belongs to a polynomial belongs to R of x such that the degree of f less than or equal to n and the kernel of phi is equal to the product fg where g belongs to R of x. Option 4, the degree of h greater than or equal to n for every non-zero h belongs to the kernel of phi. Right. Let's now get into the solutions. We have V, a R vector space of all n by n matrices where n greater than 1. V is equal to mn r, n greater than 1. A belongs to V and A is invertible. A word of caution is here that A is a given matrix from V which is invertible, but not A is any matrix of V. No, A is only a given matrix from V which is invertible for the discussion. That's all. Now, R bracket x, we all know, the vector space of all polynomials with real coefficients over R. It is given phi is a map from R bracket x to V is an R linear transformation defined by phi of x power k is equal to a power k for all k greater than or equal to 1, and phi of 1 is equal to the n by n identity matrix. Now, this implies for any polynomial p of x is equal to a0 plus a1x plus a2x square plus so on and so forth, amx to the power of m belongs to r of x. We have phi of p of x is equal to phi of the polynomial is equal to a0 times phi of 1 plus a1 times phi of x plus a2 times phi of x square plus so on and so forth, am times phi of x to the power of m. Why? Because phi is a linear transformation. Right. Now, this means a0 is equal to phi of 1 is identity. A1 plus a1 into phi of x is a because of this. A plus a1 into phi of x square, a square plus so on and so forth, am into phi of x to the power of m is a to the power of m. What is this? It is wherever there is x, you substitute in p of x. It will be p of a polynomial in a. P of a. Phi of p of x is p of a. Now, what will be the kernel of this R linear transformation phi? That is, ker phi is the set of all those polynomials px belongs to R of x such that phi of p of x is 0. That is, the set of all those px belongs to Rx such that p of a is equal to 0. Right. Note, what are the elements of ker phi? It consists of all annihilating polynomials of a. So, p of a is 0, means annihilating polynomial. So, ker phi consists of all annihilating polynomials of a, and obviously, if m of x is the minimal polynomial of a, obviously every minimal polynomial is also an annihilating polynomial. Therefore, m of x belongs to ker phi. Agreed. Now, let's call on option 4. For every non-zero h belongs to ker phi, the degree of h is greater than or equal to n. Right. This will not happen always. Right. We give a counter example. Let A be In, means n by n identity matrix, and we have n greater than 1. Agreed. Agreed. Now, h of x is equal to x minus 1 is an annihilating polynomial of a. Yes, h of a will be a minus I, that will be 0. So, it is an annihilating polynomial of a. Note that the degree of hx, what is the degree? It is 1, where 1 less than n, because n is greater than 1. Right. Now, hx belongs to ker phi. Why? Because ker phi consists of all annihilating polynomials of a. Therefore, hx is an annihilating polynomial of a. Therefore, hx belongs to ker phi. Now, let us see what are the properties of hx. So, hx, we have a non-zero polynomial hx. Hx is a non-zero polynomial because it is x minus 1. Hx belongs to ker phi, and the degree of hx is less than n. Thus, we are able to find out a non-zero h belongs to ker phi whose degree is less than n. So, this is not true. This is not true for every h. For this h, in this case, for a given a like this, right, the option 4 is not true. We move on to other options. We now take options 1 and 2. They talk about one-to-one and on-to-ness of phi. Right. Now, we go for a counter example. Again, A is equal to I2. Now, in our case, n is equal to 2 now. Right. V is M to R. Now, then phi of 1 is I2, correct? Phi of x is A is I2. Phi of x square is A square. I2. So on and so forth. What the phi is doing? Phi is sending 1, x, x square, x cube, and all these polynomials, it is sending to identity. That means phi is a many to one map. Therefore, it's not 1, 1. Clearly, phi is not 1 to 1. Agreed. Is it? Onto the same example. Onto. For any polynomial p of x, a0 is equal to a0 plus a1x plus a8x x square plus so on and so forth, amx to the power of m belongs to rx. We have phi of p of x is equal to, it is in fact a0 I plus a1a plus a2a square plus am a to the power of m, but a is I2 only. Therefore, a0 I plus a1 I plus a2 I plus am I. So, take I2 common. So, a0 plus a1 plus a2 plus am I2. What is this? It is a scalar multiple of I2. Such matrices are scalar matrices. Scalar matrices. So, image of phi will be the set of all images of under phi. That is phi of p of x, where px belongs to r of x. What is the image of phi of p of x for any p of x? It is alpha a2, where alpha belongs to r. So, that means it consists of all scalar matrices. It is generated by I2. So, image of phi is a subspace of r of x, and it is generated by I2. That means its basis is a singleton set, I2. Its dimension is 1. So, image of phi is a subspace of M2 over R. And its dimension is 1. And it will be a proper subspace of M2 over R, because the dimension of M2 over R is 2 into 2, 2 square. That is why it is a proper subspace of M2 over R. When it is a proper subspace of M2 over R, image of phi is not equal to M2 over R, and thereby phi is not onto. Thus, phi is neither 1 to 1 nor onto. Therefore, options 1 and 2 are not true. Now, we have eliminated 3 options. Option 4, now options 1 and 2. By elimination, we say our option 3 is true and our answer is option 3. That's all. But our students will ask us, sir, why not we prove option 3? Yes, we do it in the next slide. Option 3. There exists a polynomial f belongs to R of x such that the degree of f less than or equal to n, and the kernel of phi is the product, consists of all those polynomials which are product of f and g, where g belongs to R of x. Let f of x be the minimal polynomial of a. Then the degree of f of x, the degree of the minimal polynomial, is always less than or equal to the degree of the characteristic polynomial of a, that is n. So, the degree of f(x) is less than or equal to n. Now, Ker consists of all those polynomials P of x belongs to R of x such that phi of P of x is equal to 0. It is a set of all those polynomials P of x belongs to R of x such that P of A is equal to 0. That is, every polynomial P of x in Ker annihilates A. Therefore, fx divides P of x. Why? Because fx is a minimal polynomial of A. It's also an annihilating polynomial of A. So fx divides P of x. Right? Because kernel of phi consisting of all annihilating polynomials of A. So f of x is a minimal polynomial of A, and f of x divides P of x since the minimal polynomial of A divides the annihilating polynomial of A. Thus, P of x is equal to f of x into g of x for some gx belongs to R of x. Right. Therefore, the Ker is the set of all Px such that phi of P of x is equal to 0, and it consisting of all those Px means fx into gx. So Ker consisting of all polynomials which are product of f of gx belongs to R of x. Agreed. So thus there exists a f belongs to R of x, which is none other than minimal polynomial of A, such that the degree of f is less than or equal to n, and the Ker consisting of all the product fg where g belongs to R of x. Thus, we have proved option 3. Thus, option 3 is true. Therefore, the answer to this question is option 3. That is the detailed discussion of the solution of the given problem from the section Linear Algebra, which talks about a linear map from polynomials to matrices. And I feel it is a very good question. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure we are going to meet you all once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.